Hello, everybody, and welcome at this very nice uh, opportunity, uh, the start of the new semester of our practice seminar for mathematical physics. And we are against all the customs and stereotypes, kick off this winter semester with double dose of contributions. Each of them will be about 40 minutes. And this might not happen without our nice speakers, which accepted our invitation, for which we very warmly thank you. And the first speaker of today is Gwilliam, who came from the University of Massachusetts in Amherst. That's right. Pronounce it correctly in US. And the second speaker, Haugseng. Yeah, I knew it's almost full professor from Norwegian University of Technology and Science in Trondheim. So we can look forward to the couple of nice interrelated talks, which has the same roof or denominator of whatever math will be involved. And the title is BV or linear BV quantization viewed as infinite functors. The first part will be devoted to discussion of some motivations and physical background with flavor of multiple algebra, I guess. And the second will be more focused on categorical aspects of this subject. So thanks very much for accepting the invitation. And if you're ready, we're looking forward to your talks.
Okay, thank you for the nice introduction. Yeah, so I'm going to start. I'm going to be talking about some joint work that Rune and I did a number of years ago. So I'm going to start by kind of laying out the context and the sort of, I don't know, questions, directions we're trying to move in. So the path integral is this like very beautiful idea from physics. A lot of success being used as a heuristic. Of course, you can't, in practice, actually implement it in the way we're used to implementing the integrals in mathematics in the analytic context. So there's cases where you can do it, but in general, it just doesn't work the way you would like. So the very big picture behind what I'll be discussing is that there's this Batalin-Volkovitsky formalism. I will just say BV. And roughly speaking, it tries to encode the path integral. So there's lots of things people use BV for, but I want to focus on this particular aspect of BV. So I'm going to the homological construction. So you switch from thinking maybe in terms of thinking about the path integral as some piece of analysis, some way of defining an integral, to thinking somehow as part of homological algebra. Okay, so we'll get into how that works. So that's in the background, so that's some context. And then the goal with Rune was to take implementations of this framework, which is coming from physics, and to phrase BV formalism using new methods in mathematics. So for us, that's particularly something called derived geometry and higher characters. So I'm not expecting that you know what either of these really are, but I'm gonna hopefully be open to sort of being just like for gestures in that direction, some sense of them. I am going to talk as if you know some homological algebra.
Okay.
Derived geometry might be thought of as taking seriously the idea that you should put homological algebra into the very foundations. So, you can think about a lot of geometry, like differential geometry, algebraic geometry is sort of a nonlinear generalization of linear algebra, thinking about vector spaces. And then you start sort of bending them or patching them together or taking subsets. Derived geometry sort of starts, if you want, with vector spaces with DG vector spaces. And it's trying to figure out the nonlinear analogs of. So it builds in homological algebra at the very bottom. So it's sort of natural that when mathematicians got interested in BV, they thought maybe it can be formulated in this. Okay, so that's a very broad goal. So more specifically, let me say what we worked on. So I'm going to sketch our result kind of loosely in physical language. And a lot of the work we did was about making it precise enough to turn into a math signal. So what we focused on was thinking about classical free theories. So there's a collection of classical free theories. And for me, free here just means it has linear equations of motion. And if you just apply the BV formalism, there's going to be a thing called BV algebras. You take a classical free theory and you do the quantization and you take the algebra of observables in any sense, you get back something else that's a piece of actually algebra, BG algebra that's stuck to it. Say, roughly speaking, I'm here the algebra of quantum observables. So we find the formalism. Produce something called the BV algebra. And our goal is to phrase this as a functor of infinity one character. Okay, so it's easy for me to say, oh, you just apply the BV formalism, but most of the work is to actually kind of formulate this characteristic that you have an infinity one category, and this so you have an infinity one category, and so that the construction that you learn from physicists actually can be done systematically and coherently enough that you really get a functor of infinity one categories. So that's the bulk of the work, is piecing down these things carefully enough so that you actually can say something sharp in mathematical terms. So, okay, so a lot of the talk will be about trying to make that more and more precise. Okay, so one question you might ask is, free theories are probably sort of boring to me, so you might ask why there's free theories. And one answer is that sort of experience shows in mathematical physics that quantization is not a functor. You try to include interesting interacting theories, it's not functorial. So quantization is not a functor. In general. But experience also shows that if you restrict your attention to things like free theories, say in the quantum mechanical setting to quadratic Hamiltonians, you can be quite systematic and happy with your quantization. So this seemed like a good place to start, to focus on the three things, because we had a chance. Okay. So I talked about the path integral, and me making a little analogy that might also make it hopefully a little more reasonable to think about just free theories. And this analogy will also sort of be in the background later. So if you think about making the path integral is sort of defining a measure on some space. And you can kind of think about measure spaces. Let's think about measure spaces where you're building on top of the topological space. Well, you can forget down to just plain spaces. Forget the measure. And over a given space, there's lots of measures that live on it. There's not sort of a preferred measure if I just tell you a topological space general. There's no really, the analogous thing would be to think about these as spaces a little bit like theories, classical theories, when you're trying to construct a measure. There's not to say like I use measure to pick. But if you think about vector spaces, there is a sort of natural measure to choose, and that's taking a harm measure, translation invariant measure. Or a bag measure we're used to mean. That's not saying this is functorial, that's up to scale, but there's sort of a natural measure on a vector space, which is the bag measure. Okay. So free theories get linear equations of motion. So you should think about them sort of linear in nature. They're like vector spaces. So you might expect there's a natural measure of delta. Okay. So let me talk about a consequence of this construction of the functor infinity categories. One of the things we set it up, we could notice and verify the following thing: that if you focus on a subcategory, you took classical free theories, whose underlying basic solutions is finite dimensional. So that's the subcategory of these things, and you restrict your functor to it. Imagine taking full homology basically. They make things quite simple. You get a very special kind of thing on the outside. You get only one-dimensional degraded vector spaces. That's if I want to keep the answer to 3 rank 1 logicals or how I should use each one. So the free theories with the simplest, sort of the most constrained basic solutions go to a very beautiful subclass of objects. So maybe make clear for more analytically minded people, what I have in mind here are theories whose the operator that gives the equation of motion is right. So really say, thinking about things like elliptic complexes. Closed manifold. The big source of such free theories. Okay, what this tells you, in this case, is that what we're recovering is the analog of the Gwilliam. Okay. Really importantly for what I'm about to say in a second is direct sums of such chain complexes go to tensor products of the lines. It's n plus the product. It's playing the role of a determinant. So it gives you the Gwilliam determinant line. If you stick in the Dirac operator on a closed manifold, it really does get you back to Gwilliam determinant. Okay. So in this sense, this sort of consequence of our work says that BB quantization, linear BB quantization, is a determinant so this is the kind of, that's a sort of type of functor people have studied quite a bit in homological algebra and algebraic geometry and so it's a very nice thing to discover that in fact when you follow the physicist's procedure carefully enough to be able to phrase it as a functor, you discover that it has this very nice structural property. Let me remind you that of course like determinant of a square matrix is talking about volume of the image of the unit iPad or something. So that fits in very well with the idea that it's talking somehow about volumes. It's this kind of categorifying statement. And this particular example I'm mentioning about taking elliptic complexes to their determinant line fits really nicely too, because on the math side, people often talk about index theory and say T.S. Singer index theorem, you get these sort of important characteristic classes of elliptic operators. So there's just sort of mathematical analysis on this side, and on the other side, should switch sides. Did the sides backwards. So people think about the Euclidean path integral in this setting and anomalies. All the time, this is treated as sort of like a dictionary people can use, and this dictionary, this functor makes the dictionary very precise mistakes. So people often compute anomalies for Euclidean QFTs on closed manifolds by using the index theorem, which uses sort of the first term classical and the determinant line. So I'm just kind of gesturing things. I'm trying to sort of say how this point of view fits in with maybe other parts of mathematics. Please feel free to ask questions or interrupt or whatever. So I wanted to rephrase our result a little bit, specifically the one up there for this context. So instead of calling them free classical field theories with finite-dimensional space of solutions, I might call them -1 shifted symplectic e.g. vector spaces. I'll talk more about these shifted symplectic structures later. Okay, so we should think about these sort of a linear version, linear symplectic manifolds, where the morphisms we keep are linear symplectic morphisms. Linear maps that fit nicely with the preserve the symplectic structure. This category here can be understood as this category if you prefer to think about it in the language of symplectic geometry. And we're saying that the quantum observables here, if you want the cohomology, is a version of a determinant line, determinant functor going to gradient lines. The reason I bring up this reformulation, partly to just give you some context, is that Bono, Martin, and Jan Pullman, Martin, there's probably a lot of Martins. It seems to be a very popular Czech name. Okay. I've been thinking about a very similar context, but they're a little more ambitious than we are. Instead of maybe, so I'm emphasizing right here, taking linear symplectic morphisms. They're interested in something more like Lagrangian correspondences. This kind of thing should be a. I think about there be something like a Lagrangian correspondence between the shifted symplectic spaces, maybe more generally some sort of coisotropic thing. They allow, they call generalized, which means they equip L with a half density. So you can think about these as being kind of, if you, so it means have half density. So the data of a pair L and rho, you can think of as formulating some kind of quantum operators in some quantum system. And they're thinking about how that intertwines with the BB formalism, which would encompass a lot of structures that we're not talking about here today. So it's quite interesting. But they also don't have an infinity one category. So there's sort of like, it's an interesting generalization. We're trying to figure out the infinity one kind of setting would be a really productive thing to do. So that was the context and motivation. Now I will introduce linear BB quantization. Any questions while I raise?
A very quick question. Why do you call this Gwilliam determinant line? The name Gwilliam.
So Quillen explained how to associate a determinant
Mhm.
line to every Fredholm operator.
Uh-huh. Okay.
So you might have seen like the determinant of a finite dimensional vector space.
Mhm.
I don't know, it's like the top exterior power of the vector space. And if it's a graded vector space, you take this alternating tensor product.
Okay.
But like when you have an infinite dimensional vector space, you can't take the top exterior power.
I see.
So Quillen figured out a way that if you had a Fredholm operator between two infinite dimensional vector spaces, because it's Fredholm, its kernel, its co-kernel are finite dimensional.
Mhm.
That makes sense. And so you could take the determinant of the cohomology, but he managed to do that over the space of all Fredholm operators. So actually a kind of line bundle, which is not obvious thing to do.
Okay.
And so you can use that when you're studying physics and families, like when you're studying the free fermion theory on a closed manifold, varying the metric gives you a different Dirac operator. So you're moving
Mhm.
the space of Fredholm operators.
Okay.
So it plays this Quillen determinant line plays a big role in analyzing things like families of fermionic theories in some background, that background being the gravitational background, or maybe choice of varying gauge field, like as a background. Okay, so we're going to do linear BB quantization in two ways. So, start to the top. There's only two parts, so get to listen to Runa soon. So I talked about BV quantization is coming from the path integral, but first I'm going to tell you a different story. Well, the last thing will be about the path integral story. First, I'm going to do it like Heisenberg would. So there's no path integral. We're going to use Heisenberg computational relations. Okay. So before I do the BV version, I want to remind you sort of the traditional way of getting a describe an analogous outcome in quantum mechanics. So recall the following way, sort of set up the basic structures. In quantum mechanics, so this is going to be, we're going to model ourselves on this in just a moment. So think about like just a plain unshifted symplectic vector space. D omega. I want you to have in mind something like D star Rn, or a point in there. We've maybe picked coordinates like Q1 up to Qn for position, and then P1 to Pn for momentum. And that symplectic form is this dpj slash to the conjugate variables. So that's sort of the input. That's like the role of free theories. Like here we're just doing kinematics, if you want. This data you can use to make a Lie algebra. Called the Heisenberg algebra. This Heisenberg algebra depends on V and omega, and it's an extension of a vector space viewed as just an abelian Lie algebra. So a zero bracket, central extension. There's some short exact sequence of Lie algebras. And in this Lie algebra, the bracket of two elements x and y from V is just defined to be, you stick them into the symplectic pairing, and you multiply this. Great. So down here, in our specific example, this says that Pi Uj equals delta Ij times C. And maybe you prefer to use C as C is H bar. You're thinking about, or I H bar, you're thinking about the traditional Heisenberg commutation routine. This is just some slick way of talking about the Heisenberg commutation relations in a coordinate-free way.
Only one times H bar. One is not in your algebra.
Sure, maybe. That's like a central element, so I can multiply it by a number, one. So I'm not missing it, maybe. I could just call C H bar if you really wanted that to be H bar. Okay. So now there's a universal thing to get an associative algebra. Remember, we'd like to have an associative algebra in quantum mechanics of operators. There's a way of taking the algebra and getting an associative algebra. Called the universal enveloping algebra. So let me call this I's. And I take the universal enveloping algebra. Over here for this example, I don't know, some people call it the Weil algebra. But the point is that we had a commutation relation here, but over here we're in an associative algebra. So I can actually say that Pi Qj times Qj Pi equals C. Like I said, C to the H bar. H bar. The point is that over here we have relation of Lie algebra in here. Now here we're saying there's a non-commutative product in this associative algebra. If you set C to 0, if you specialize C to 0, they do commute. So you get back to the usual classical algebra functions. So I just want to point out that although I talked about a specific object, this can be easily upgraded to just functors in the traditional. So you can make a category of symplectic vector spaces, define a functor to Lie algebras, called I's, and then you can apply this universal enveloping algebra that goes to associative algebras. This functor actually sits in an adjunction. If you have an associative algebra, you could just remember the commutator bracket. So there's a forget functor this way. And this happens to be the left adjoint. So I bring this up because I'll do something parallel in a minute. But I think it's useful to think that the way we start with a symplectic vector space and get the Weil algebra, this thing we study in quantum mechanics or use in quantum mechanics, the P's and the Q's that don't commute, is this two-step process. This is a way of making the algebra of quantum operators starting in a linear setting. So the BB formalism, if you look at it carefully, does something parallel with shifted homological degrees. So I talked here about ordinary vector spaces and ordinary algebras and ordinary associative algebras, and now I want to go to the DG setting. And the DG setting thinks I have a Z grading, so I can also do kind of shifted analog. So I'm going to write something on the board first, and then talk a little bit about what it means. So sitting inside, there's a category we call quad one on our paper, but sitting inside of it are one shifted symplectic vector spaces. That means the pairing over here, instead of preserving cohomological degrees, mixes cohomological degrees. So since it's the pairing is degree plus one, if I take something degree 0 and degree minus 1, I can pair that gets them non-zero. And quad one just allows Doesn't have to be non-degenerate, but also pre-symplectic structures. Similarly, this means Lie algebras, but where the bracket has a unequal degree. I'll give you an example of all this stuff in a minute, but the whole point is just like that story, but I should have added this one shift to things. So there's a functor I'll call Haugseng. It takes a one shifted symplectic vector space and makes a one shifted Lie algebra. Okay, and then this is the weird thing over here. So there's a thing called E0 algebras. I'll talk about that in just a second. But the point is that there is a natural adjunction between one shifted Lie algebras and zero shifted algebras. So let me say what I mean a little bit about this. So alg E1 is the fancy name for the homotopy coherent version of an associative algebra. So when you move to the world of homotopy theory or chain complexes, you don't necessarily ask for your things to be associated on the nodes, but that there's an associator and then maybe kind of a thing that relates the associators. We keep going. So that's what this homotopy coherence data. Sometimes people use a particular model for this known as A infinity. But the one has to do with the fact that in an associative algebra, there's one way of multiplying things. There's a generalization of associative. So alg E1, an element of alg E1 is kind of a homotopy coherent associative algebra. There's a thing called En, and this means an object here, A, has n compatible homotopy coherent multiplications. With n directions of multiplication, or the model you might have seen, if you've ever heard of this before, is the little index. People talk about it in topology. But you can think about it just having n directions of multiplication, like maybe a vertical one and a horizontal one. So most times people think about adding more multiplications. E0 is going to be when you have no multiplication. You have zero compatible homotopy coherent multiplication, so alg 0. An element of this, A, is an object with a unit, so some distinguished elements in it, but no multiplication structure. So if we were thinking about it in chain complexes, A would be a chain complex or cochain complex, say over a base field K, along with a cochain map from Ka, picking out a distinguished element. That's the unit, if you want. So this is one of the weird things about BV, is that somehow in the end you're getting an algebra with no algebra structure. It's just something with a distinguished. So but first, let me tell you the takeaway. So this composite functor, U0 of Haugseng, some input data like this agrees with, or agrees with the quantum observables you construct for V omega using the VD function. What we did is we looked at what one did in the VD function, and then we just realized that you could write it as a composite functor the way we've done here, or there, the usual associative algebra. I guess, given what I said over here, I want to make a remark that that this U0 thing is actually pretty interesting. So I'm actually justifying this U0 enveloping functor is an important part of our work. So this Fortunately, I'm not going to tell you too much about it, but there is an adjunction. So every Lie algebra, shifted Lie algebra, is going to give you an E0 algebra. And if you have an E0 algebra, you can forget it down to a Lie algebra. And how does that really work? Well, let me tell you the forgetful behavior first. So we've got this pointed object here, right? We've got maybe a chain complex A with a chain map from the base field. Where does it go? It goes to A mod K as an abelian Lie algebra. DG Lie algebra. Shifted DG Lie 1 algebra. So it has no bracket. If something has no multiplication, you can forget it down to a Lie algebra with no bracket, with a 0 bracket. Okay? But the functor the other way is quite interesting. If you start with a shifted Lie algebra, what you end up taking, the model of U0 is the Chevrolet-Allenberg coaching complex of G. So this is the thing that models Lie algebra covariance. So this is a very old functor, like at least 80 years old now. But I think it's a relatively recent thing to realize it's part of an adjunction that's similar to the enveloping algebra forgetful adjunction. Okay. So I've been saying a lot of abstract things. Let me write down the simplest, interesting example, just so it doesn't seem completely abstract. And to give you a sense of what I mean by this shifted stuff. So I want to start with something with a one shifted symplectic pairing. So in degree 0, I'm going to put a copy of R with a basis element X. In degree -1, I'm going to take a copy of R with basis element C. And the bracket, well, since it's a degree +1 bracket, the only way I can get the degrees to work is when I pair C, X, and that'll be 1. All the other pairings are 0. That's the degree of omega is 1. Okay, now let's make the Haugseng. So the Haugseng here has a graded vector space and this element D. So this part's in degree -1. These two parts are in degree 0. And I define the bracket between X and C, well, to be omega of X and C and C, which is C. This is very similar to doing the Haugseng from before, but with this degree shift. I'm just going to tell you, when you take the Lie algebra chains of this thing, that looks like a symmetric algebra on this Haugseng, where the differential depends on the bracket. And I'm not going to explain all the ins and outs of that, but let me just tell you the answer in terms of this. So I take sim on this means the polynomials, the free commutative algebra generated by these things. So this looks like R, adjoining X, T, and C, where the differential is D squared So C times d by dx. Which, if you have seen the BV formalism before, this looks like H bar times the BV plus. If you've seen it before. In general, it takes the algebraic chains. If this thing always looks like, because in the shift we're doing here, sim of G, where the differential extends the bracket as a second order differential operator. The bracket goes from sim 2 of G to G when it's one shift. Okay. If you want to know more, talk to Martin or Brana. They can give you lots of examples. Okay. Maybe I should remark that our construction here is part of a chain of junctions where you can replace 0 by n here and the Lie shift by 1 minus. So there's a way of making these higher dimensional, having n multiplications by having a Lie bracket and a fun one. I have a second way of making BV, but I've been talking for 40 minutes and I don't want to cut into too much of your time.
You should go on.
Okay. So the takeaway is that linear BV quantization is a lot like Heisenberg's commutation relation. It's just the finding degrees. Okay, so now let's do it. Construct BV quantization like Duran and Kazul. Okay, so this is to try to connect it to the path integral. Okay, so before I try to describe the BV way of doing integration, let me remind you that there's already a way we do integration using homologic algebra in math. That's called the Duran complex. So, Duran complex already encodes integration. Homologically. So let's do the model case, which is really easy to see everything, and then I'll extract BV from it. So suppose M is a closed, oriented, n-dimensional manifold. Then there's this chain complex called the Duran complex. There's 0 forms, which are smooth functions, 1 forms. And now, top forms are the things we talk about integrating. So in fact, there's a map, since M is closed and oriented, called integrating over M that goes to the real numbers. Okay, it takes the top form and just integrates it. I want to point out that this is a coaching map, where you think about putting 0 on the 0 differential. Okay, so the map from top forms given by integration factors through its cohomology. So this not has to factor through those top forms might will be the image of D. So D of B minus 1. Okay. If M is connected, you should think of the connected case, then in fact this is one-dimensional. So given a top form, computing its cohomology, this is H and Duran momentum. I take a top form and I put its image in cohomology, that's the same, essentially the same data as knowing its integral. So taking cohomology is integrating in this setting. And this, let me just point out for those of you coming from physics, this is like integrands. And then you're just remembering the relations you get from integration by parts. So it's kind of algebra. So this is how we do homological integration in math. Now, in physics, you're in a slightly different setting. In physics, when you're doing the path integral, you've fixed a measure. So in the path integral, when you pretend you have it, you have a measure, which, all it takes in physics to create something is to write a symbol for it. So you just write something like E to the I, S to the H bar, D phi, you can pretend like everything's good. You have a symbol. Okay? But, okay, so I'll use mu for measures as a shorthand. So suppose we're on this manifold and we fixed an actual measure mu, so a smooth platform. This is, I'm going to assume that's it. And mu, suppose it vanishes nowhere. So it's a volume form. This kind of thing, if it made sense, would also be a volume form, right? This is supposed to be a limit type measure, doesn't vanish anywhere. This doesn't vanish. So what happens if we have mu? Well, I want to point out that we can try to piggyback on top of what we already did. So since I have mu, there's a canonical map from functions to top forms, okay, which just sends a function here. So this function times mu. We just multiply it by your choice of volume form. And now we have this integral over m. So we get this composite, which sends f, of course, to the integral over m of f of mu. Let's think about, in physics, this path integral is supposed to be normalized to be a little bit like a probability measure. So let's suppose that mu is a probability measure. So let's say it's a probability measure that has integral 1. Then in that case, this thing here is exactly the expected value against mu of f. Maybe you might like this notation. Okay. So computing the expected value of a function on m with respect to this probability measure is again like fitting into this homological story. So you can factor it through the Durand thing. Let me show you how to do it in a little more detail. Here, we know we had top -1 forms using the Durand differential. I claim you can also fill in something here. So take the vector fields on so sections over m of the tangent bundle. Well, there's a natural map here parallel to multiplying by mu, which is contracting. So I'm going to this. So it's going to send a vector field. That goes to the contraction of the vector field with mu. I have a top form and I contract a vector field today. I got a coordination one form. And so there's an operator from here to here to make this a even square called the divergence operator. It's a vector field. And since this is a commuting diagram, we know that computing the expected value of f is the same thing as looking at its image in smooth functions modulo divergences. Just totally parallel with this. So we could compute expected values homologically, as looking in the cohomology at this co-kernels. Okay. This thing just keeps going to the left. So over here you can do what I'll call a polyvector field, so that's sections over m right to the tangent bundle, and that'll map to omega n grades. And you again just use contraction with So the upshot is there's a polyvector field complex whose differential is divergent against mu, and it's by construction isomorphic to the Durand complex in mu. And I claim that this complex is what people write down in BD. That's the kind of thing you do in BD. You have functions on the fields, and then you have linear functions in the antifield. So let me We do a specific example. I told you this story about how to cook up this polyvector field complex that's secretly a copy of the Drame complex. If M were actually just a vector space, all the algebra for the chain complexes works fine. What goes away is that the cohomology is no longer concentrated at the top, one-dimensional. On a vector space, it's not compact, so I can't do that integration story. Let me just wrap up by describing. You can do this using polynomial functions and polyvector fields. When M is just a vector space. I'm going to do an example for you. Here's my example. Suppose that M is the real line. And I take my measure to be the Lebesgue measure, dx. Well, then I'm going to do these polyvector fields. So in degree 0, I'm going to take the algebraic functions, R join x. On degree -1, I'm going to write the polynomial vector field. So I'm going to use the notation C here. C here is a frame for the tangent bundle that corresponds to d by dx, that vector field. And it's a fun thing to work out that the divergence operator for the Lebesgue measure, this divergence operator for the Lebesgue measure, you work it out that a divergence operator for the Lebesgue measure is d squared dx dc. Okay. Which is up to this factor of c, the same operator we wrote here. Okay. So again, this is the BD Laplacian. And I'm going to say that in general, this construction, these two constructions of BV are compatible. We started with V in ordinary vector space, V in ordinary vector space, with the Lebesgue measure. And you did this thing I just talked about here. You did the polyvector fields, the divergence against the Lebesgue. That's the same thing as if you took T star 1 of V, that makes it a one-shifted thing with a standard symplectic form. And then did this things of the Heisenberg thing. These two things are similar. So this story we told about the Heisenberg thing actually matches very nicely with the divergence operator story. Okay, so the upshot is that this construction I talked about at the beginning, up to sort of making the obvious shifted symplectic space out of something, really is about secretly just ordinary integration. So that's the motivation. It went on a really long time. And I tried to give you some sense of this with very explicit computations people do, which are sort of the toy versions of the things people do in physics. The real crux of the work for Runa and I was to work all this stuff so it actually fits inside of infinity categories. So that involves using operad theory, model categories, and tools from higher categories. So it's kind of wonderful that, in fact, the physics prescription does admit such a precise formulation. And maybe it also explains why physicists maybe hadn't set up these kinds of higher categorical ways of thinking about BD. Okay. I think probably I should just stop. So thank you for listening.
Thank you very much. I don't know, we can maybe open a very short question panel, or if you wish to continue smoothly. So is there any intermediate question? Not, we can continue immediately. So doesn't seem to be the case. So yes.
seconds of time, so get no.
Maybe I would have a question to our online audience. Is the Blackboard seen properly? Because there are some questions around this.
Yeah, for me it works fine, thanks.
Okay, thank you. Don't worry to complain in the meantime, so I'll try to adjust it. Okay. Yeah. There's only 40 minutes left until other guys will kick out of the room. So just
Sorry. I'll try and not go for the whole time, but yeah. Yeah, so what I thought I would do is to try and give sort of a conceptual description of what we actually do in the paper to construct this linear BV quantization of a functor. I'm not sure I would be able to say it in language that makes sense to people here, but feel free to ask questions and hopefully Owen can translate. Right, so this is sort of how we probably should have done this in the paper, but we didn't really understand higher categories well enough back in the early days when we wrote this paper. Right, so we had this infinity category that Owen mentioned called quad P. You say, I'll say that I work over some base field K of characteristic 0. Generalizing a fraction a bit, but I think that's probably enough. And then I'll try and write chain complexes of K, but this really means the infinity category of what we get from the chain complexes of a K by inverting the quasi-isomorphisms. Okay. So this infinity category I can define as a pullback. This is just a forgetful functor that forgets this map to the shift of K. And here I'm supposed to take the second asymmetric power of something shifted by minus P. Well, what does that mean? The object here is some V and V complex over K. And then there is some map omega from lambda to V by minus P into K shifted by minus P.
So right, so 5P is this pullback category.
Yeah, so
In the
find
category
this
of
as
categories, yeah.
pullback.
In ordinary category of categories.
In the infinity category of infinity category.
Ah, cool. Even better.
It's really easy.
But yeah, okay. But the point is that obviously, yeah, you can write down this diagram and you can take a pullback. But you should think of the this as being like this, and then a map would be a map of chain complexes plus a chain homotopy between the corresponding symmetric forms and the things. Right. So what we sort of want to construct here is a functor Haugseng Lie algebra functor from quant P to P shifted Lie algebras. And again, this will be in the category of PG Lie algebras. After inverting that quasi-multiples. So we want to build this by thinking of this omega as determining, given this the omega, we should think of this omega as determining central extension of the abelian V algebra on this same complex V. And so instead we sort of want to use this omega to sort of to define the bracket, like I'm going to take V plus K with this new central element, and then like the bracket of V and C is supposed to be omega of VC. Then
No, not C. You don't want C there. V and W or something. C is central, right?
the bracket of W is omega of V and W times C.
Yes, thanks.
So anyways, so and this becomes a P shifted Lie algebra because we had this P shifted form. If you get the shifts right, which I may or may not do on that. Right. So how do you do this central extension more conceptually? Like in this derived setting, that's kind of a nice way to think about that. The central extensions in the ordinary sense, you can correspond to cocycle, like degree 2 cocycles for Lie algebra cohomology. So we can sort of that fits quite nicely into this picture by this junction that I will mention between Lie algebras and chain complexes with the left adjoint. So this is surely unlike exchange functor. And the right adjoint is the abelian Lie algebra functor. We have this adjunction, and then I take the circular change on the abelian Lie algebra. And what you get is sim of x shifted by 1. And so well, now I have to say this lambda 2 of something. I can think of it as getting the symmetric square of x shifted by x shifted by 1. So I sort of go from the odd to the even case or vice versa, and then shift it back down by -2. So so I can think of this omega here as giving me a map from sim2 of V 1 minus P to K shifted by 2 minus P. Then, well, this is just one part of this direct sum that is sim of V minus P. To project to the degree 2 part. And so now this left-hand side here is the Schiller-Engberg change on the abelian Lie algebra on V shifted by -P. So what this map, this composite amounts to. Therefore, this is the Lie algebra chains. And so in the map up here, it's like dually, it's a cocycle in the Lie algebra co-chains of this in degree 2 minus p. Like that, and cocycle in the algebra cohomology here 2 minus p on the abelian algebra on G is equal to so we have the adjunctions. I have a map out of the left adjoint of this Lie algebra mapping to something, and so this can transform into this way. It transform this into a map from the abelian Lie algebra P minus P to the abelian Lie algebra on N shifted by P minus P. And then out of this map, I can construct this central extension by formally by taking the fiber of this map. Otherwise, I have this map of Lie algebras. P minus P and this fiber will be the central extension that we call minus P omega, except where this is, except we have a shift, so this is the P shift in the algebra, shifted by minus P, so we have an unshifted the algebra. And so, like, why is this a central extension? Well, you have to sort of work out what this pullback amounts to, but somehow you see, since we only have this quadratic part in the map, there is no linear part. This is sort of the zero map on the underlying object. So this fiber sort of as just a chain complex. This is given by taking V minus P plus minus P. Now I'm right, I didn't get the shift right.
There should be one more shift because you're in like a cone type thing. Like the K thing should be just it's like one, right?
That just gives me 1 minus P.
So yeah. It's an exercise for the audience to get the shifts right.
I mean, yeah, like if P was 0, I should have something in degree 0, right? So that's no. This implies that P from 0 you should have an extra thing. I'm confused about that, but maybe it's better just fine. Right. So this is sort of, but like this is a very perceptual way of constructing this shift in Lie algebra. So it sort of automatically makes it functorial, and so we get this Heisenberg functor.
Sorry, I don't understand how can I get this functor out of this pullback? To use the upper arrow and what else?
Sorry?
How can I get this functor? I don't get it. This Heisenberg.
I mean, it's just it's the fiber of a natural transformation coming from this bar P.
The data of omega gives you that right map.
Yeah, and this map is determined by omega.
And so then taking fullbacks is a
So
it's like
I can sort of, omega was what omega is this map.
Mhm.
And then I compose this with this projection. And then I use the adjunction to
use the ejection afterwards to get
so sort of all these operations are sort of just like functorial by nature. So there's just you don't really have to do anything to make it functorial. It's just like we observe that it is this finite lattice that depends functorially on B and omega.
You wrote down a composition of functors. So
Yes, definitely.
which is
So so then we have this. So we have this nice functor. So taking this in the case of p equals +1. And we have to go from 0.1 to E1. And in this case, we define a developing functor to something called BD algebras that I don't want to explain. So this is not involves adding a power, adding a variable as far, where so if we set this equal to B1, you end up with this E0 algebra that was orange torque. So an E0 algebra in chain complexes just again complex with an K. And like this composite you can identify as taking the Schiller Eigenvalue chains on a one shifted V algebra shifted by -1. Then this map from K is just coming from the fact that if you take the Schiller Eigenvalue chains on 0, you get a map from you get K. So it's sort of the function is thinking it's just automatically such a map, she's just giving you that. Yeah, so that would be like this. But then we can also set each part to be 0. This is a E0 algebra. So that's a shifted Poisson algebra. Like in general, a Pn algebra that's shifted Poisson algebra, so you have commutative multiplication, and then you have a compatible Lie bracket that's 1 minus n shifted. So P1 algebra is just an ordinary associative algebra. An ordinary Poisson algebra. And then, so the reason for the numbering convention is that Pn is the homology of the En operand for n greater than or equal to 2. So so we can so the idea is that we can think of this composite from point 1 to E0 algebra as a sort of quantum observables, and then this one which is expressed to 0 is kind of like a classical observables, which is in this case a one shifted Poisson algebra. And then this composite is just sort of the obvious way to go from something with a Lie bracket to sort of freely adding the commutative multiplication on this. So enveloping P0 algebra on that and P1 algebra.
and in practice, it just looks like taking the symmetric algebra with a shift.
Right. Yeah. So
You just have the symmetric algebra.
I guess it is like the underlying functor is just sim, right?
Yeah.
Yeah. Right, you just take sim to get the commutative freely add the commutative multiplication, and then I guess the shifted Lie bracket just kind of extends to sim. Yeah, I will say. That's what I wanted to say about the construction of this functor, and then I'm going to discuss a little bit the sort of shifted version of this free theory quantization. So I have this diagram, and So Owen mentioned this notion of the N algebra, which you can think of as just like having n compatible associative algebra structures in a homotopy sense. And so we can just take the whole diagram star and sort of take the n algebras in this diagram. So, but these are all symmetrical modal functors. Means that they use a new diagram where I just look at en algebras in all the terms. So, yeah, I'll maybe just omit this BD part because I don't have anything to say about it. Now we have, well, here you can say it's en algebras in zero algebras, but that's sort of the zero part is sort of we automatically have a unit in the en algebras, so sort of en algebras in the zero algebras. It's the same as en algebras. And the point is that we can identify more concretely all of these terms. So, for example, you can show that en algebras in V, like say n-shifted V algebras, you can show that this is equivalent to 1 minus n-shifted V algebras. If this equation d to n. And then these en algebras in quad 1, we sort of have, well, we have at least a sketch of an argument that this is equivalent to 1 minus n. But this induced diagram gets here down here, the 1 minus n shifted one as in the algebra functor. And then the result of Samsonov.
Just say Safanov, it's fine.
But that's, yeah, Well, also say wasn't doing, but he didn't know what about it. Yeah. This is the same as PN algebras. And then it ought to be the case, but I don't know if
There's also a functor, right? I mean, you have to get the functor.
Sorry?
You get the functor from Lee 1 minus n to LHPN, right?
Right, so that's what I wanted to say. You get this functor, and I feel like this should be sort of the universal developing PN algebra. But I'm not sure we have. I'm not sure if that is like proved. So by this I mean, you have a shifted Lie algebra again. You just sim to get a commutative multiplication, and then extend your shifted Lie bracket to get a 1 minus n shifted plus 1 algebra. So what we get is that we get a kind of shifted quantization that goes from quad 1 minus n to produce the n algebras in so, and for n equals 1, we have a zero shifted thing here. We have an unshifted Lie algebra, and then E1 is this associative algebra. So this really should be the Weil algebra functor for n equals 1.
So like I might talk, I motivated our BB thing by starting with the n equals 1 case.
Right.
And now you're saying.
So then we should be able to recover that from, I guess this story is a bit work in progress, so I don't want to make too strong assertions, but yeah, this composite has to be this functor. What else could it be? And so for like the higher version, you sort of get like a Weil en algebras. And
This is the race.
So the last thing I wanted to talk about, I'm trying to be a bit brief, but I wanted to say something about how this shifted quantization should somehow fit into the framework of extended TQFTs and sort of combined with other things, you can get a sort of like quantization of linear AKZ theories in a certain sense. So so but I don't know how familiar this extended TQFT story is. I don't really have time to moderate it very well, but like, but the idea is that, well, you know, mathematically, like you can construct an infinity n category, broad and oriented. So infinity n category where the I-morphisms, so I estimating to n are I-dimensional oriented relationship quantums. And then the composition of these isomorphisms is given by including these different things together. Maybe now I can be slightly helpful and say what happens in the case n equals 1. So then we have the objects will be oriented zero manifolds, and the morphisms will be oriented one manifolds with boundary. So and the boundary is divided into source and target components. So most of them might look this kind of thing. And then you know, this I've decided that this is the source part of the boundary, this is the target part of the boundary. And then if I have another such one-dimensional cobordism whose input is three things, then I can compose them by gluing. So here's another cobordism that goes from three things to one thing. So the composite of those two in this category would be the manifold you get by gluing them. And then we sort of add on surfaces going between diagrams like this as the two morphisms and high dimensional manifold and all that. I should say details exception of this is 3.5. Okay, and this has a symmetric monoidal structure, a tensor product given by the taking the distant union of all the manifolds. Then you can define an extended T15 to be a symmetric monoidal functor for an extended oriented then functor from this board and oriented to some target symmetric monoidal category. So So depending on the kind of PQFT, sort of, there might be different choices you might make for this target X. The one that's I would consider here that's relevant here is the thing called like the Morita. The Morita in the N category of the N algebras. And this works out of any symmetric monoidal C, such as K complexes, any reasonable C. So like it has the objects En algebras in C. Morphisms are En minus 1 algebras in bimodules in C. And En minus 2 algebras in bimodules, and then we kind of keep going up to the N morphisms being N-fold iterated bimodules in C. Again, I could mention to be slightly helpful, okay, as n equals 1, so then we have associative algebras, the objects, and then we have bimodules between them as the morphisms, and then composition of some of these bimodules as morphisms is given by taking relative tensor products. So if I have sort of M is an AB bimodule and N a BC bimodule, then the composition is N tensor over B with N, which is an AC bimodule.
We have about 10 minutes left.
Sorry?
10 minutes.
So we had this BVE quantization functor, and that was like nice and symmetric monoidal, so it gives us a functor from this Morita in category of quant 1 to Morita in category of chain complexes. And then so we sort of want to have a way to get from this Boltzmann category into this Morita in category of quad 1. The objects here we saw were, well, the objects here are En algebras in quad 1, which I said earlier were the same as quad 1 minus N. So the objects in here are the same thing as the objects of quad 1 minus N. So you might hope that there should be similar descriptions of the everything in this category, so that we expect to be able to construct a functor from like a linear Lagrangian category and a linear Lagrangian N category into this by taking dual. So sort of what should happen is, well, on objects here would be like shifted symplectic. So N minus 1 shifted chain complex, and the object that should be sent to is the dual as with its dual 1 minus n shifted pairing. And then if I have a Lagrangian correspondence from E to V prime, what should happen is that L dual becomes a bimodule for V dual on V prime dual when you regard this dual pairing as actually coming from an algebra in quad 1. So if you believe this, you can get a sort of I think I will say like okay, so you can construct a functor from this Boltzmann category to a category of oriented cospans in spaces. So basically what I mean by this is that I take, I have a cobordism X, and what I want to assign to it is the homotopy type of X, but then also the maps I get from the incoming and outcoming boundary parts. Then the oriented cosine part means that I also remember the fundamental classes of all these pieces in my cobordism. And so this is constructed in a paper with Steinbach. And then given one of these linear symplectic spaces, you should be able to cook up a functor from that to this linear Lagrangian, which is kind of like an AKZ construction, like some G omega. But it seems that it's a little bit ridiculous to call it an AKZ construction because this is just like a baby case of the real thing that, it's kind of just saying, I have this V, and then I have X, then I can construct, my fundamental class on X will be a map from, I can think of it as a map from cochains on X, relations in K, to K, with 2 minus V, which is the dimension of X, and then I can get a, so this AKZ construction should give me cochains on X with coefficient in V, with a pairing that arises by combining omega and this orientation class. And the others, I don't write it out, but it's sort of, so it's a composite of a couple of maps you naturally get from those 2 pieces of data. So sort of combining all these things, you should get from the symplectic space V omega gives you an n-dimensional oriented T2T by starting with port N, then we go to this cospan, and then linear Lagrangian category. And then we have this sort of dualization thing that lands in more n1. Then go to more n of, much more precisely, we could have we have this E0 structure here, so I can think of it as being chains under K. So we sort of have algorithm pointed by modules actually. And we could go to more n of E0 algorithm K. So this would kind of be the, I don't know, so this functor is maybe like a classical field theory, or maybe this one is, and these are like the classical observables. And then this functor is supposed to give us the quantum observables about theory. So it's obviously like from a physics perspective, it's like a very silly or baby example of a field theory, but it's like, it will be quite, still work in progress, but it's sort of an example where you can really write down, an explicit functor that is the classical field theory, and then have this quantization of sort of a functor like this. Okay, I am way over time, so thanks a lot for your patience.
Thank you very much for a great work. Thank you, both of you, for great contributions, and we're too unfortunate to have enough time for many questions. So let me open a very short discussion panel if you have a question on your mind right now.
It would be a question to both of you. When you go in the construction from V algebras to developing E0 algebras, you use the Schwab-Youngberg construction. So in the Schwab-Youngberg homology, there is a graded commutative product. So does that? I think you're not using it here.
So that algebra chains is a co-commutative coalgebra,
Yeah.
but it's not a DG commutative algebra. It's just a chains is a coalgebra.
Yeah. But are you keeping track of that structure?
You can. It's the analog of the fact that the universal enveloping algebra, Lie algebra, is a co-commutative coalgebra.
Okay.
So there's the same thing for all these EM things. It's also a co-commutative coalgebra.
It would be EN algebra in co-commutative.
Coalgebras. Yeah. So it's a kind of bi-algebra.
Okay. And does that, I mean, that product is, like, if you look at the bottom of the classical observables, right, you can think of that product being modified by the Poisson bracket towards the non-commutative algebra. So I can see that somehow you get both the quantum version of the observables and the classical one with the Poisson bracket. But do you capture this notion of infinitesimal deformation of the commutative product by the Poisson bracket in the construction?
I think the answer is yes. It's like we're using the data of that Poisson bracket,
Yeah.
like the P0 bracket, say, to determine the E0 deformation. So the differential in the Chevrolet chains is determined by the bracket on the Lie algebra, right? And that bracket on the Lie algebra is the Poisson bracket on the shifted Poisson algebra. It's like the same data.
So it's encoded in the differential.
Yeah, in BB quantization, the deformation is by deforming the differential.
Right. Okay.
And then by applying this alg-n functor, it should, if you unravel it, which is kind of hard to unravel, you would see that it's deforming the product structure.
Okay. Okay. Thank you.
So it's especially to the extent that you can take. So how do you see, like, is there any way to see what happens when we change the orientations? In other words, can you see like some version of evolution necessary?
If you change the orientation, that would correspond to just changing the sign. No, it's like you change the sign of the fundamental class, so what you end up is that, like, then as you get your AKs and pairing at the opposite sign. That's the symplectic structure you're gonna have on this code change in X would be like B minus the one you had with the alpha.
Quantization.
Can I make a comment? This includes like a billion BF theory and a billion transcendence as examples. So it's like not totally empty of interesting examples.
Okay, any other question from the online audience? If not the case, let me thank the speakers again.
First part I didn't remember. It's good to see.
Now